Alright, good evening again everybody, and as always thank you for to those of you who keep the camera on. It's really helpful, so I really appreciate it. So today, before we move to the next topic, there are a few things that I want to mention. So the first one is that someone asked me about the rubric and the schedule for the presentations, and I just published the assignment on Canvas. So if you go on Canvas, you should find the assignment, which is a project peer review. I'm going to open here right now. So yeah, it's the presentation peer review actually, and then within that assignment you can find the Excel file that you will use to do the peer evaluation of the presentations. Just a reminder, I'm going to share the screen so I can better explain. Screen to share. So this is the file that you will find on the first sheet. You will see the actual rubric, and remember that you will need to fill this column by column, from left to right, so we don't make confusion on who comes first. And then on the second page, on the second tab of this file, you can also find the order in which all the presentations will occur. So I just realized that I didn't publish the assignment was already there, but I just needed to publish, so I published it now, and then you can find it here as well, in that assignment. I was also looking at the calendar for the last few sessions that we have. So today is the 21st, right? Yeah, today is 21st, so we have today, then we have Wednesday, then Monday we will have the second midterm, and then the last 4 lectures we will have the presentations. So my plan now is today to talk a little bit more about continuous systems. Last time we talked about the string. This time we will talk a little bit about beams. So we increase a little bit the level, and then next time, which is Wednesday, is the time before the midterm, I'm planning to do a little bit of Q&A. So I would say you can think about questions that you have about the last topics that we saw, or whatever we saw during the semester. This is because the midterm will be comprehensive, meaning that I will include probably one problem plus questions. So the questions could be open answer questions, or let's say or multiple choice questions, and these questions can be about whatever we did during the semester. The problem will probably be more focused on what we did in the second part of the semester, so starting from 2 degree of freedom systems. But the questions, again, multiple choice and open answer, can be about anything that we did during the semester. So again, please think about questions. If you want, you can send me the questions in advance, via email, and ask me, to talk a little bit more about some topic, or directly Wednesday, during the lecture, you can ask me questions, and I will, we can have a little bit of discussion. Make sense? Also, another thing, again, for the last 4 lectures, when we will have the presentations, I would like to remind you that I will not be able to record them because of this nightmare that Zoom has been during this semester. So the attendance is actually required for these last 4 lectures. So make sure that you can come, and then you can so that you can evaluate the other students. I think someone has a hot mic. Yeah, so let's make it a little bit more cold. All right. Any question about this? Sure. the presentations are due, yeah, the 23rd. I did this so that you could have a little bit more time to prepare for the midterm, because I know that if I put the deadline, let's say Friday, you will spend probably just Saturday and Sunday to prepare for the midterm. I think you should spend a little bit more time preparing for the midterm. Makes sense? If you study, it's not hard. Other yes. Yes, so I'm planning, I didn't finalize it yet. I'm planning to include one problem, which will be a little bit more focused on the second part of the semester, which means from 2 degrees of freedom on. And then there will be a few questions that can be either multiple choice or open answer questions, and these questions will be about anything that we did during the semester. So starting from the simple harmonic oscillator up to basically what we are doing now, which is the vibration of a continuous beam. Sure. No. This is just the midterm, the second midterm. Next Monday, the 28th. Yeah. So it's 1 week from now. And this is also why Wednesday I don't want to do anything new, so that whatever we cover today, you have at least 1 week to go back and review and think about what we are covering now. Other questions before we move on? Alright, as I mentioned before, if you have questions on few topics, on something that we covered during the semester, please either send me an email, between the next class, or next class, come here and ask me the questions. Alright, I guess we can move to the last thing that we will cover this semester. So we started to talk about continuous systems a couple of lectures ago. The first thing that we looked at talking about continuous systems is the string. So string is probably the most simple, again, continuous system, because in that case we only look at forces that are in one direction, which is the, let's say, the axial direction of the string, and basically nothing else is involved. Nothing else is kind of responsible of the motion of the string, except of course some initial condition in terms of displacement or velocity. Now we are going to move a little bit forward. Today is 21st. Because we are going to talk about beams in a transverse vibration. Now, when I talk about this, I need to specify that we talk about beam in transverse vibration, because when we look at a beam, which is like a structural element where typically one dimension is much bigger than the other two, so we can kind of analyze it as a 1D element, we can have actually in the real world, we can have also vibrations in the axial direction. We can have also torsional vibrations for a certain beam. So in this case, we are focusing on what's going on in the transverse direction, which is a kind of, basically, if you think about it, is a kind of extension of what we study in Structures 1, because in Structures 1 we look at axial load, then we look at torsional load, we look at transverse load, and we could do the exact same thing when we talk about vibrations, because we can have transverse vibrations, we can have axial vibrations, we can have torsional vibrations, and so on. We're not going to have time to cover all of them, but what I would like to focus on, I think for us, for aerospace engineers, the most interesting that we should look at is transverse vibrations. So, as always, we start from a certain schematic. So the schematic that we are looking at is, for example, a cantilever beam. So a cantilever beam means that the beam is fixed on one side and free on the other side. So this is our beam. We can look at a certain length, L, of the beam. We also need to look at a certain coordinate system. So we have the axial coordinate that we typically indicate with letter X, and then we can look at a transverse coordinate. We can call it Z, for example. And then also in the transverse direction we will have the quantity that we are interested in, which is the deflection in the, of course, transverse direction. Also, we can assume for now that we can have a certain load in the transverse direction. Transverse means transverse with respect to the axis of the beam. So when we talk about a transverse load, it is a load that is perpendicular with respect to the axis of the beam. So again, if we want to kind of generalize, here we have a certain load. Again, this load for now doesn't have like a specific function, it's just a load that varies along the axis of the beam with a certain function f of x and t in this case. So this load here, this function f of xt, describes whatever is going on the beam in the transverse direction. And of course, since we are talking about dynamic loads, we have that this load changes with x, which means it changes in space, but it also changes in time. So we have to look at both variables, length and time. So we have to find the equation of motion for a system that looks like this. When we want to find the equation of motion for a continuous system, what we need to do is to basically extract one small portion of our beam, look at the internal forces and internal moments, and write the equilibrium equations for these internal forces and internal moments. So let's assume that we extract. Of course, I'm going to zoom in so we can see like a bigger version of that infinitesimal portion of the beam. So let's assume we are undergoing a certain deformation on a piece of beam. So what we have, again, a certain load. And then what we need to look at also are all the forces, all the internal loads that are on one side and the other side. So one side and the other side of the infinitesimal portion of the beam. So what are the internal forces that we need to look at when we analyze the transverse motion? Any idea? Tension and compression are internal forces, are like two faces of the same internal force, and they are both related to axial loads. in this case we are looking at the transverse loads, right? Let's make sure that we don't make that confusion. Again, right now we're looking at the transverse, so we're looking at whatever is going on in the perpendicular direction with respect to the axis of the beam. So the internal loads that we need to look at are internal bending moment and internal shear force. So this curved arrow here indicates the internal bending moment at the section X, and then this arrow here indicates the internal shear force at the same section. Our little portion goes from X to X plus dx, so dx is the entire length. So we need to see also what's going on the other side of the portion of the beam. We also have the same internal force, internal loads, so we will have the internal shear force, which in this case is V plus dV, because we are at cross-section X plus dx. So the internal force changes a little bit from one point to another one, and the same is valid for the bending moment. So we have M plus dm. Yeah. What increases? Well, when you use like this infinitesimal notation, this is to indicate that there is a change in something. In this case, we have a change in the internal shear force that goes from V to V plus dV, and then a change in the internal bending moment that goes from M to M plus dm. Now, when you go from one location to another one, depending on what type of external loads you have, your bending moment can increase or decrease. Your shear force can increase or decrease. Now in this case, we are just indicating like plus dm to say that there is some change from this location to this location here. Again, can be an increase or decrease depending on how the external load is applied on the beam. Make sense? So now we are talking about, again, dynamic loads. So it means that looking at the internal forces or internal loads is not enough. We also need to consider the inertia force, because when you apply a certain motion to a body in general, you will have also some you have the external force, which is indicated by these little arrows here, but you will also have some inertia. So if we assume that the beam is moving, let's say, upward, we have that the inertia force is against this motion, so we can have an arrow going downward. How do we characterize this inertia force? I'm going to put like a star here, so I have more space. So here we have the inertia force depends on the so it's basically the product between the mass and the acceleration, right? So we can also do something similar to what we did with the string, where we introduced the linear density. So in this case, we can also write the product between mass and acceleration as rho a dx. So this would be the mass of this small portion of the beam, because it's basically linear density by excuse me, volume density by the cross section by the length, and then we have to multiply this by the acceleration. So we multiply this one by the second derivative of the displacement, which we can indicate here with w in dt. So this is like lowercase w. So rho a dx will be the mass, and then d squared w in dtw will be the acceleration in the vertical direction, where this lowercase w is the displacement in the vertical direction. Make sense? Any question about this? So, when we want to derive the equations of motion, having the correct schematic, the correct free body diagram is crucial, because if there is something wrong in the free body diagram, the rest of our derivation will be wrong as well. So please spend 1 minute to review this one, think about this, and let me know if there are questions. So basically you are asking about the direction of this moment here, right? Okay. Yeah, that's a very good question. Here I included the directions of the bending moment on the left side, bending moment on the right side, shear force on the left side, shear force on the right side. Now these directions here are not like random directions. These directions come from a convention that is established about the direction of the internal forces when you have this orientation for the two axes, for the axial direction and the perpendicular direction. Now, this is something that we cover in Structures 1. So if this is a little bit blurry about the directions, I suggest to go back there and look at these directions. Again, these are picked by convention, but this is something that comes from from the initial classes, basically in structural analysis. So on this side, these are the positive directions. On this side, these are the positive directions for shear force and bending moment. Other questions? Okay, if there are no other questions, I would like you to spend actually a few more minutes now on finding the equation of motion. Actually, let's talk about equilibrium equations for this small portion of the beam. So basically now from this schematic here, we need to write two equations. The first one is the equilibrium in the vertical direction. The second is the rotational equilibrium, because in order to have full equilibrium of this body, we need to make sure that we have equilibrium in the vertical direction, but that's not enough, because we need to make sure that we have also rotational equilibrium. So please spend a few more minutes on trying to write down these two equilibrium equations. Alright, let's try to do a little bit of reasoning together on what we have to write now. So we said that we need to write two equations. One would be the equilibrium in the vertical direction, which means summation of forces in the y direction is equal to m times a. So what are the forces that we have in the vertical direction? For sure, we have this force here, this shear force that is applied on the portion of the beam from the left side. We also have this V plus dV also applied on the right side, and then we have the external force. So the terms that we include in our equation are minus V plus dV. So minus V plus dV, this is going down, so with respect to our global coordinate system it is negative, so minus V plus dV, plus we can add the external force, so we gave like a generic function f of x and t times dx, because remember this is a force per unit of length. Let me actually write it down here. So since it is force per unit of length, and here we are doing equilibrium of forces, we have to multiply this force by a certain length, right? So plus, here we have the force on the other side, and then this will be equal to m times a. We already found before what m times a is, so it is equal to rho a dx, and then the second derivative of the deflection, d square w in dt square. Now the second equation that we have to write is a summation of moments equal to 0 in this case, because we assume there is no rotation, so summation of moments equal to 0. Same thing. Now when we do moment equilibrium, we have to select one point with respect to which we want to calculate the rotational equilibrium. In this case we can use this point to calculate to write the equilibrium, the rotational equilibrium equation. So in this case we have, so we start from this one, m plus dm. Then we have the contribution of this force here to the moment, is the shear force on this side, so this will be negative v plus dv multiplies dx, because remember we are doing equilibrium of moments. In this case this is a force, so we need the force multiplied by a distance, so the moment of this force with respect to this point would be the force times this distance, which is dx. So that's why I wrote v plus dv times dx. Then we have to add the contribution of this distributed force, so the moment of this distributed force with respect to this point, which is also force times distance. So in this case we have plus f of xt times dx, so this will be the force. What about the distance? How much is the distance between this distributed force and this point here when we look at distributed load? It is the midpoint. It is a distance between this point here and the midpoint. So we have to multiply this quantity by dx over 2, right? And then we have to also look at the contribution of this moment here, which is opposite with respect to this, so we have minus m, and then equal to 0. We don't have any applied moment, so that's why it would be equal to 0. Any question about these two equations? So now that we have these two equations, we need to play around a little bit in order to, come up with our equation of motion. So what we should do first, we should write the changes in shear force and bending moment. So here we have this dv, here we also have dv, here we also have dm. We can now write these in terms of derivatives. So, because when we write them in terms of derivative, then it will be easy to compare with all the other terms. So, let's write that dv is equal to dv in dx times dx. So, this will be the partial derivative with respect to the coordinate x multiplied by this distance here. And we can do the same with the moment, so we have dm will be equal to dm in dx times dx. Because basically when we write the changes dv and dm in this way, we can relate these two changes with the change in distance that we have from this x to this x plus dx. So now that we have this dv and dm, we can plug dv here and here, and we can also plug dm here. So basically we need to rewrite these two equations with these two quantities here. So we obtain minus v minus dv in dx times dx plus f of xt plus v, and then equal to rho a dx. This doesn't change, so we have the second derivative of the displacement with respect to time. Let's do the same for the second equation. So in this case we have m plus, now this dm becomes this one, so we have dm in dx times dx. Then we have minus v dx, and multiply this term by this term here. And then we have this dv here, so minus dv dx. So I'm multiplying here these two, and then we have plus f of x t, the x squared over 2 minus m equal to 0. Let me check if I've am I missing a dx? So I'm talking about this one. No. So here we have v, so this is dv in dx times dx, so we replace this one with this one, and then we, what am I missing? There is no dx here. This term is the force, so the force is already this one, is v plus dv. Here we don't have dx. Here we have dx because this is a force per unit of length. So when you have this is already a force. This is a force per unit of length, which means that in order to obtain the force, you have to multiply this one by a certain distance, a certain length. So here we don't have the x. Same thing here. This is already a force. So you don't need to multiply this by the x. Make sense? So for this one, v stays like this. Then when I get this one, dv, we change this dv with dv in dx times dx, which is what we have here. So this actually transfers. So we have the dx, this comes from here. And let me check, I think I have everything else. So this term is here, this term is here, and then we have the acceleration, and then we have m plus this one was replaced by this one, so it's there, and then we have v dx, and then we have dv dx, and then we have f xt dx squared over 2 minus m equal to 0. I think we have everything. Now, can we simplify this a little bit? Where? Which is this one? Oh, okay, this one. Okay, this one. Alright. Okay. Sorry. Are we good now? Still not good? What else am I missing? Alright, so can we simplify these equations? I think we can. For example, here you can see that here we have this v which is negative and this v which is positive, so they are the same v, so we can get rid of them. Also here we have, so once we get rid of these two here, we are left with this term, and this term. All of them include this dx, and now we can actually get rid of that dx as well. When we look at this equation here, we can also simplify the equation, because we can also get rid of this m and m here. We can also get rid actually of terms that are like a higher order differential, because if you have like a differential is already a small, quantity. If you do the square of that is even smaller, so you can get rid of that as well, which means we can get rid of this term here. And here we multiply these dv and dx, they are also very small, so we can remove those as well. So once we look at this, we can rewrite these two equations in a more simplified form. So sorry, I need to change page, I don't have space anymore. So let me write down the new version of the equations. So the first one becomes minus dv in dx equals to plus f of xt equal to rho a d square w of xt in dt square. Now, of course, all these equations, now I can even write all these equations, these functions like the shear force, the external force, and the displacement are all functions of both the space, so depending on which point along the axis we are looking at, and also function of time, because once we have like an external force that changes in time, everything else also changes in time. The second equation becomes dm in dx. Again, this is also the internal bending moment, is also a function of x and t, minus the shear force, again also a function of x and t, equal to 0. Now again we have to recall a little bit what we did in structures 1 when we're looking at transverse loads, because we know there is a relation between bending moment and shear force, right? Do you remember what the relation between shear force and bending moment would be when we look at these two functions for a beam? Right, which one is the derivative of which one? We can look at, so the derivative of the moment is the shear force, so we can write as dm in dx equal to v. So the derivative of the moment is the shear force. Remember, when we were looking at the shear force, we start from the load diagram, then we can integrate that one, and then we can obtain the shear force, then we can integrate one more time, and then we obtain the bending moment. So if we go, backward, if we start from the bending moment, we derive the bending moment, and we can obtain the shear force. So this is the relation between the two functions, shear force and the bending moment. Now that we know this one, we can actually apply this in our two equations. So we can basically reduce the number of variables that we have, because these two equations are related to each other by basically this relation here. So we can write as negative d in dx of, basically we replace this v with the derivative of the moment. So we have dm in the x, of course the moment is always function of x and t, plus f of xt equal to rho a, then the second derivative of the deflection, and this dt square. For the second, so basically from this one again, of course, we are calculating the derivative of the moment, which means that we have the second derivative of the moment. So we have negative d square m in the x square of xt plus f of xt equal to rho a, and then as always the second derivative of the deflection with respect to the time. Now remember that when we were looking at the equation for the string, our goal was to determine the relation basically between the deflection in the vertical direction and the tension basically that we had together with, of course, at some point we included the initial conditions as well. So our goal, of course, in this case, when we look about transverse vibration, is to determine the displacement in the vertical direction, so the displacement in the transverse direction as a function of the external force. So this equation shows already the deflection here. This w is our function, is a function that we want to determine, because it shows in form of acceleration, but that's not enough. We need to also find a relation between this quantity here, so the bending moment, and the deflection. Now, we already have actually, again, going back to what we did in structures 1, we already have a relation between the bending moment and the load. Does anyone remember that relation between the bending moment and the load? Excuse me, the bending moment and the deflection? the moment is actually the second derivative of the deflection, and when we were looking at this relation, we also need to look at the material properties and also the geometry of the cross-section, because we were looking at the Young's modulus of the material, and we were looking at the moment of inertia of the cross-section. So the relation between bending moment and deflection in the transverse direction is the following. So we have that the moment, which again in this case would be also a function of x and t, like we saw before, is equal to the product between E and I, and then, as we said, the second derivative the x squared. So this is the product between E, which is the Young's modulus, so it has a material property, and this is I, which is the moment of inertia, so it depends on the shape of the cross-section. When we put these two together, Young's modulus and the moment of inertia of the cross-section, what we obtain is called flexural rigidity. I hope these concepts are coming back from previous classes. So now, what we have here one term, which is the second derivative of the moment with respect to x, and here we know that the moment is the second derivative of the deflection also with respect to x. So how can we relate these two? If we take this one and we replace here, so we plug this here, what we obtain is simply the fourth derivative of the deflection with respect to x, because if this is the second derivative of the moment and the moment is the second derivative of the deflection, it means that this term is the fourth derivative of the deflection. So the last step that we have here is so the equation that we have here is the equation that basically tells us how a certain beam subjected to an external transverse load would vibrate. So basically this tells us how our function w, changes with x and t, where x is the axial coordinate and t, of course, is time. So spend please 1 or 2 minutes to look at this equation, and then we will do a little bit of physical reasoning on this equation, and we can start to see what should we do next once we have this equation here. So let's start to think a little bit about this equation here. So first of all, what kind of equation is this? It is a fourth order partial differential equation. So it is first of all, it's a partial differential equation because the unknown that we are looking at is the deflection, this W here that shows up here and here, and this deflection is both a function of space and time. So this is something that we have in common with what we saw for the string, because in that case we also had the deflection as a function of space and time. So this is in common between the string and the beam. The main difference between the string and the beam is that in this case we are looking at a fourth order partial differential equation, because in that case we had that both terms were second order derivatives. In this case we have this fourth order derivative, which means that the equation is a fourth order differential equation. Also, of course, in that case we were looking at the important parameter was like the wave speed, which was the ratio between the tension, the internal tension, and the linear density. In this case we are looking at external force. In that case we didn't have any external force, we can add, but for the case that we saw we didn't have any external force. In this case we have the external force, and this of course shows up on this side of the equation. So this is what in this case would drive the motion, would drive the deflection, the deformation in space and time of our beam. Also, another thing that we should look at, in comparison especially with the string, is actually this term here, this EI. When we talk about a string, doesn't really make sense to talk about flexural rigidity, because if you look at the string, there is no flexural rigidity. It means that the cross section of the string doesn't provide, with respect to the entire length, doesn't provide an actual rigidity, an actual moment of inertia. But in this case, when we look at the beam has a cross section. When we look at the cross section of the beam, we look at the moment of inertia of the beam itself, which means that if we look at the material as well, when we look at these two quantities, we have the flexural rigidity of the beam. And of course that has an influence on when we look at the static analysis, the flexural rigidity has an influence on the deformation, the deflection, and when we look at the dynamic analysis, that term has an influence as well. Does it make sense? Another big difference between the equation that we saw before for the string and this equation, can anyone think about another difference between the two? So once we have the equation, at some point we need to solve the equation, right? So what would we need to solve this equation here? Which means that what do we need to solve the equation? We need boundary conditions and initial conditions. Remember, in this case we are looking at a function like the deflection, which is function of both space and time, which means that we both need initial conditions and boundary conditions. the initial conditions are related to time, the boundary conditions are related to space. Now, in this case, how many conditions do we need? Exactly. We need 4 boundary conditions and 2 initial conditions. We need 4 boundary conditions because we have a 4th order derivative here. And then we need still two initial conditions because we have the second derivative of the deflection with respect to time. In the previous case, we needed 2 and 2, actually, even if we eventually gave like the function of the deflection for the initial condition. But if we look at this case, we have again we need 4 boundary conditions and 2 initial conditions. So how can we determine the boundary conditions, for example, in this case? We have to look if it is fixed or free, or could be pinned, for example, or we can have some let's say spring, at one end of the beam. So what do we need to look at in general? How do we call all these things? Supports, or we can call them constraints, because depending on how our beam is constrained, we can determine the boundary conditions. And typically, when we look at beam, we need to look at 2 conditions on one end and the other 2 conditions on the other end. If we take 2 conditions from one side, the other 2 conditions on the other side, it will make 4, and we can find the 4 conditions that are needed for solving our problem here. So what kind of constraints can we have? We can have on one side, for example, the beam is fixed. How do we determine, like, mathematically the condition for a fixed constraint? So, for example, if we have something, let's say, that looks like this, just pretend that it is a straight beam. So this, what kind of beam is this? This is a fixed because it is fixed on this side and also fixed on this side. So what kind of boundary conditions would we have in this case? We will have 2 on this side and 2 on this side. So what are the 2 conditions that we would have on this side and the 2 conditions that we would have on this side? Say again. Well, we talk about static condition, so basically the same of the static analysis, but we need to look at the conditions on in mathematical form. So we need to look at physically what these 2 constraints do and translate that to a mathematical form. This is what I'm asking. So if we have like a beam that is fixed here, what does this constraint do to the beam? Exactly. If we look at this case, we will have on both sides, because it's the same constraint, no translation and no rotation. Which means that this point here, at any time, because we are doing dynamic analysis, cannot move up and down because it is fixed, it is clamped, and also cannot rotate. So it means that the deflection on this side, so W of 0t, would be equal to 0. So at any time, no matter what we put here, the deflection will be 0. But we also have that the rotation will be 0, so this cross-section cannot rotate, which means the first derivative will be equal to 0. So we'll have that dv in dx as 0t will be equal to 0. Of course, on the other side, same constraint, but instead of being here, we are at the end, so we have w of lt is always equal to 0, and the first derivative in dx of lt is also equal to 0. So this is an example of what type of, and remember we have to have 4 of them, because with these 4 boundary conditions we can solve our problem. Let's look at another example. Let's see, we can do fixed on one side and pinned on the other side. What kind of condition are we going to have in this case? So on this side, of course, it's going to be the exact same that we had on the previous example. So here we had zero displacement and 0 rotation. So we have w of 0t is equal to 0, and the derivative in x of 0t is also equal to 0. But what about this side now? This is pinned now. So what do we know? In this case, the deflection and the moment will be 0. So this condition is actually the same. So we have w of lt equal to 0. But then we have the moment that will be equal to 0, because we know that the pin is a constraint that cannot transfer any moment to the beam. We know the relation between deflection and moment is like the second derivative. So we have that the second derivative of the deflection at L, so at any time, will be equal to 0 always. And we have a lot of examples. So we could look, for example, at the cantilever beam. So you know the 3 most common cases that we can find in terms of constraints are fixed, pinned, or free. So if you have one of these 3 cases, then you can combine them in different ways. We can have free on one side and fixed on the other side, which means that we have a cantilever beam, or we can have a pin on one side and a simple support on the other side. This will be like the 4th type of constraint, or any combination of these constraints, and then we should be able to determine the conditions, determine 2 conditions for each of these type of constraint, which means on each beam we can come up with 4 conditions that can help us to solve, to find the solution of this equation, which means find the, for the 4th order differential equation. Makes sense? In terms of, this is about boundary conditions. We also need initial conditions. So for the initial conditions, we can do something similar to what we did for the beam, for the string, which means we can give a certain deflection at one point, for example along the beam, or we can set initial values of velocity or deflection for one of the 2 ends of the beam. For example, if we have, let's say, a cantilever beam, where one end is free, for that free end we can set a certain value of initial deflection or initial velocity, and by having these two, or both actually, by having these two values, we can combine these two values of, for the initial conditions with the four values for the boundary conditions, and we can solve the equation. We can find a particular solution with these values of initial and boundary conditions. Does it make sense? So now for this case we are not going to have time to go through the whole solution of the equation, but actually, since we already went through the solution of the string case, do you remember what type of technique we used for the string? In that case, we use a separation of variables, which means that we found some way to split basically our differential equation in two differential equations, one where we see only time and the other one where we see only space. Now, in this case, we can do the exact same thing actually. The only difference is that in that case, we came up with one second order ordinary differential equation in time and a second order ordinary differential equation in space. In this case, we will come up with a fourth order ordinary differential equation in space and a second order ordinary differential equation in time. This is the only difference between the previous case, the string, and this case for the beam. But beside this, the process is actually very similar. We should come up with like an equation that is, a function that is a product between two functions, one in time, one in space. Then we calculate the derivatives, we plug in our equation, we rearrange so we can split, we equate to a certain constant, and then we can split into separate equations, and then we can look at the generic solution and so on. But what I wanted is to show the approach that we use to find, basically the equation of motion for a beam versus a string. And of course, the next step would be to look at a plate, for example, where instead of having only x as a variable in space, we would have x and y as a variable in space. Or for this beam, still one-dimensional, we could look at torsional vibrations or axial vibrations, which are actually a little bit more simple than what we see here, but that would complete the discussion about beams. Make sense? Alright, this is what I was planning to cover today. So we have actually one more minute. So if you have questions, please ask your questions. Yes, if the density changes in time, I'm trying to think about a situation where the density, because I can think of a change of density with temperature maybe. That is more for a fluid. Here we talk about solids. Something that would, again, changing density, I think less likely to happen for, a solid structure. What can actually happen is that for example, this quantity here, where is it? Like this quantity here, the moment of inertia, in this case we assume to be constant, like a constant quantity, which means that we are looking at a beam that has like a constant cross-section from one side to the other one. However, you can have a beam that changes the cross-section from one side to the other one, which means that I is not a constant anymore, and you have to look at, instead of having a constant I, you'll have I of x, for example, where your, again, moment of inertia changes from one side to the other one. That would make our equation a little bit more complex, which means that in this step here, we cannot bring this I outside of the derivative because it's a function of x as well. This would be like one example where, you know, this equation can be more complex. Makes sense? Or, for example, if you have a beam that, in this case, another assumption that we made is that E, the Young's modulus, is the same over the entire beam, but we can have situation where we have beam made out of multiple materials, for example. In that case, you can try to find like an equivalent Young's modulus for the entire beam, or you need to find a way to see how the Young's modulus changes, you know, from one point to another one. Makes sense? So yeah. Okay. Well, yeah, in that case, probably a different approach is needed to find these equations, because maybe you will need to kind of, you know, analyze this structure with like two different bodies connected. In this case, we are looking like one single body subjected to an external force, I would say. So I'm open to have even a little bit more discussion. However, we you know, run out of time for today. So it is 8:47. Again, we're going to meet again Wednesday. So if you have questions about you know, things that we saw during the semester, please feel free to either send me an email or ask directly next time. Again, if you have other questions about this, I can stay a few more minutes and then we can have. But if you don't, and if you have to leave, feel free to leave, and we are going to meet next time. All right. Thank you very much.